My guest today is Professor Gabriele Veneziano, who is a professor of string theory, who is a pioneer of string theory. He has conducted most of his scientific activities at CERN and held the chair of elementary particles, gravitation and cosmology at the Collège de France in Paris till he retired. Welcome, Gabriele.
Thank you.
Thanks for doing this. So I want to start with one of your papers, a quantum universe before the big bangs, plural. And you say the predictions of general relativity have been verified by now in a variety of different situations, setting strong constraints on any alternative theory of gravity. Nonetheless, there are strong indications that general relativity has to be regarded as an approximation of a more complete theory. So our dreams of grand unification has not yet happened. Looks like general relativity and quantum mechanics play different games. They don't play well together, and they play at different scales. So this has been a problem, right? So when you think about quantum universe, so this is sort of a different view of the more conventionally held Big Bang theory, right? So what do you mean by that?
Well, yes, indeed, as you say, the old picture of the evolution of the universe, which is based on Einstein's general relativity, which is, by the way, a theory which ignores quantum theory. In that theory, as you run back in time from today, you find in our past, some 13.5 billion years ago, a point in time, an instant at which everything, blows up. The temperature of the universe becomes infinite, the density of the universe becomes infinite, the space-time curvature, because space-time in general relativity is not necessarily flat, that also becomes infinite. And so the old traditional view is that that instant is the beginning of time, and that's called the Big Bang. This was the old dogma. It went on like that until the early 80s, when people realized that that model has big shortcomings. In particular, this Big Bang had to be, what we say, extremely fine-tuned, namely the properties of the universe just after this event had to be fine-tuned to extreme precision in order to explain our present universe. Otherwise, the evolution from that moment until now would have produced a universe very different from ours. In fact, a universe where there couldn't possibly be human beings or life. So a new paradigm came up in the early 80s, which is called the inflationary paradigm. And in that scenario, there is a certain era, a certain epoch in the evolution of the universe where when the expansion of the universe is so rapid, it's exponentially growing, and that's why it's called inflation. And in that picture, this is what the important point I want to stress. The role of the Big Bang is completely changed, and I'll try to explain why. As you know, as the universe expands, it cools down. Okay. Near the Big Bang, the temperature was extremely high. Today, the temperature of the so-called cosmic microwave background is a few degrees above the absolute zero. Now, during inflation, since the expansion was extremely rapid, the universe, if it had any temperature before inflation, it became extremely cold, okay, and empty. And this is why, you know, this scenario, this is very typical of this inflation. However, we know that the universe had to be hot at some point in our past, because unless the universe was hot enough, certain phenomena could not have happened, like the creation of light nuclei, what is called Big Bang nucleosynthesis. And so we know for sure that there was a moment in which the universe was very hot. But whereas in the old scenario, that initial temperature was actually infinite, in this other picture, in the inflationary picture, the Big Bang comes at the end of this inflationary phase. How? Because you say, well, the universe was very cold at the end of inflation. How can it be? How can you explain this hot universe? Because of quantum phenomena. There are some quantum phenomena which can be calculated in this inflationary scenario, which warm up the universe by creating a lot of particles. Now, this creation of particles is absolutely a quantum phenomenon.
So let me ask a quick question,
sure.
Gabriele. So, if I understand this correctly, there appears to be two issues. One is, as you say, in the conventional view, if there is no inflation, things have to be extremely fine-tuned based on what we see today. So that's sort of problem number one. Problem number two is the temperature issue, right? So with inflation, everything got really cold. But then we don't really know what was happening pre-inflation. And so inflation is, without knowing a lot about it, Gabriele, it's so sort of throwing a blanket on the problem that we can't really quite explain, isn't it?
Yeah, so I think you're right. Okay, I mentioned one problem, which was this fine-tuning. So the fine-tuning can be avoided thanks to this inflation, because the inflation produces a universe which is very homogeneous and very flat and so on. So, and this is what is needed in this initial state of the universe to explain our present things. Then inflation does something else. Throughout the inflationary phase, quantum phenomena occur, and first of all, they produce, on top of this extremely homogeneous universe, tiny quantum fluctuations. And then inflation is capable of amplifying them precisely to the level at which these perturbations can explain the present structure of the universe. So quantum mechanics actually intervenes twice in the inflationary scenario. The first time, because during inflation, it produces fluctuations which become later on our galaxies, our stars, and so on. All our structure comes out of this fluctuation. However, there is also the problem of the cooling down, and you need a hot universe at some point. And that is some quantum phenomenon of a different type. It is called the reheating phase of the inflationary scenario. It marks the end of inflation and the beginning of the standard cosmology. So this event in which inflation stops, the universe reheats, and normal evolution of the universe starts, this is the new Big Bang of this modern cosmology. So in modern cosmology, the role of the old Big Bang, which is the beginning of time, a singularity because everything becomes infinite, that moment is now redefined as the end of inflation. So it doesn't take much to understand that if the Big Bang becomes the end of inflation, the Big Bang is no longer the beginning, okay? Because it's the end of inflation. Now, another mystery is what happened before inflation. That's a different story, okay? So the first point I'm trying to make when I say quantum universe before the Big Bang is that in this modern view, the Big Bang, one, is not the beginning of time. Two, is a quantum phenomenon, this reheating. And before it, the inflationary phase was full of quantum fluctuation because they produced the inhomogeneities that we see now, amplified, evolving, and so on and so forth. So if you want, all these quantum phenomena, if you want, are before what is usually considered the initial time. So with this Copernican revolution and the Big Bang is no longer the beginning of everything, is if you want, is the passage from the inflationary phase to the normal evolution of the universe.
So the inflationary phase, Gabriele, is it fair to call it a inflation hypothesis? Because we don't really have any mechanistic reasoning for inflation, right? We just say inflation happened and that's that.
Well, no, that is not very fair.
Okay.
I mean, let me say that the first model of inflation, believe it or not, is due to Einstein. It was as early, I think, as 1917, 18, that he invented the idea of a cosmological constant. Now, the reason why Einstein introduced the cosmological constant is not what we need in the normal inflationary theory. It was because this constant gave a repulsive force which counteracted the attraction, the gravitational attraction. Einstein wanted to have a static universe because at that time people did not know that the universe expanded. And he realized that without this additional term, the universe would collapse, would not stay static. So he introduced something, he fine-tuned the value of this cosmological constant just precisely to have a static universe. So he did his own scene of fine-tuning. Then, once it became clear that the universe was expanding, Einstein himself called this, I think, the biggest blunder of his life. But this is to say that it's not difficult within general relativity to have a kind of energy, which is now also called dark energy for reasons that we can go back to, a kind of energy which instead of producing attraction produces repulsion. Now it is precisely this type of energy that can give inflation. And it is relatively easy to find, very sound, completely consistent models which give this, exponential, very rapid expansion of the universe. This is not a problem. Now, however, if you push me harder and you ask me, but then do you know exactly what produces this kind of cosmological constant or dark energy that gives this accelerated, because the real thing is to have an accelerated expansion of the universe. What precisely gives it, then we don't know yet. We call it generically an inflaton, a kind of field which fills up the universe in these early stages and which produces this fast growth. And there are many, many models of inflation. However, once you say, okay, I like this model for this and this reasons, then within that model, you can work out the consequences. So believe it or not, we can see what happens during the evolution of the universe before this newly defined Big Bang. Because you can compute these perturbations because they are fixed by quantum mechanics. You can see how they evolve. You can see them in the inhomogeneity, in the fluctuations of the temperature of a microwave background today, which is measured, it's at the level of 1 part in 100,000. And you can study, these are the experiments which go under the name of MA or Planck, the Planck satellite.
So if I understand this correctly, Gabriele, so in the quantum universe, what you're saying is that during the inflationary phase, there are a lot of quantum fluctuations.
Yes.
And that is what we see in the CMB. That's what we see in visible structures today in the universe.
Exactly.
And even in that, when you rewind time all the way back to time equal to 0, you still have a need for some sort of an initial quantum phenomenon, right? For the universe to start off.
Yes. Well, you need somehow, okay, to start inflation, you need some conditions. Now, so the beginning of inflation, this is where opinions differ and we don't have a firm theory. And for instance, I have my own pre-Big Bang scenario, but okay, once you say that within a certain patch, because it doesn't have to happen everywhere in the universe, but within a certain patch, certain conditions are met, then inflation starts, and then you can follow the evolution by, very reliable techniques, including this reheating at the end of inflation. The simplest model is to have what is called a scalar field, like the Higgs field, which has a certain potential energy, but gradually this energy in the inflaton field goes down slowly, until at some point this inflaton decays, if you want, disappears, and that is this transition from inflation to the ordinary cosmology. And this decay of the inflaton corresponds to this reheating of the universe. And you can even compute, how much you reheat. So what will be the temperature after the inflaton has disappeared and all sorts of particles have been created. And that temperature can be large, can be too small, but certainly is not infinite. You can really do a calculation. If any, many models have too low reheating temperature, so they have problems, for instance, having Big Bang nucleosynthesis. So, but this is just to emphasize there is nothing infinite about this. Now, what is still mysterious are the initial conditions that led to inflation. This I agree, and I think most people who work on the subject agree to.
Yeah, so there's still scope for God, in the sense that we still don't know how that was all put together at the beginning.
Yeah.
So can we, so we are at about 13.5 billion years post the start of the universe. The data that we have now, can we retrace that back and have some expectation of what this quantum fluctuations, sort of, I don't know what the right term would be, but the quantity and the duration or whatever, can we have some expectations of what that might be?
Those quantum fluctuations you're asking?
During inflation, yeah.
Well, okay, perhaps I didn't quite get the question. I mean, you are asking about today, what
Yeah,
has
I was
happened to
wondering.
them, or how do they will evolve in the future, or
I was wondering if there is some sort of a property of that inflationary phase that we can back compute from
oh yeah,
today's information.
yeah. I mean, as I said, once you accept a certain model of inflation, for instance, you say I have a certain scalar field which has a certain potential and slowly moves, changes smoothly in time, then you can compute these quantum fluctuations, which you can, really know at each length scale, there will be different fluctuations. So you have a spectrum, what we call a spectrum of fluctuations. For instance, the typical spectrum of fluctuations of inflation is what we call a nearly flat scaling invariant spectrum, namely at every scale there is roughly the same amount of perturbation. Actually, inflation predicts a slightly red-tilted, what we call red-tilted spectrum, namely large-scale fluctuations are a little bit larger than short-scale fluctuations. And this has been measured, in the CMB, and we know that there is indeed a small deviation. Another prediction of inflation is that there should be also primordial gravitational waves produced during inflation. These have not been seen yet. That would be really a fantastic proof, if you want, that gravity was quantized, what was not classical like in general relativity, but had to do with quantum theory during inflation, because precisely quantum mechanics predicts the amount of these primordial gravitational waves. And people are looking into this. These are not like the gravitational waves observed by LIGO. This will be a stochastic background of gravitational waves, which really, fill up the universe like the stochastic background, if you want, of electromagnetic waves, which is nothing but the cosmic microwave background, except that, as you know, gravitational waves are much, much harder to detect than electromagnetic waves. And so this, people are trying with these very sophisticated interferometers to see whether this background exists. It's one of the aims also of new projects like LISA and so on. So these are all very specific predictions, generic predictions of inflationary theories. They differ, for instance, in the amount of these tensor perturbations. So the fact that we have not seen them yet at some level already excludes several inflationary scenarios. They are no longer viable because they would predict a background of gravitational waves which is not seen, which is too high, and it has not been seen. So it's not science fiction. The interesting thing is that looking after the true Big Bang, this moment of preheating, looking before the Big Bang is not science fiction. It's something you can actually check. in
So,
experiments.
so these are potentially testable hypotheses with LISA and more powerful LIGO in the
Wow, like a ET, the Einstein telescope. Yeah. Mm-hmm.
and so the fact that you mentioned here, it's a lot of quantum fluctuations happening during that inflationary phase, as opposed to one big bang.
Mm-hmm.
There has to be fingerprints between these two ideas, right? That we could test in the gravitational waves, and and uh, and pick one that appears to be more correct.
Mm-hmm. Uh, as I say, I mean, the end, uh, the end of inflation, this small bang, let's call it, instead of big, because there's nothing infinite about it, creates the microwave vector. The cosmic microwave vector is an image of that explosion, except that very much diluted because of the subsequent expansion of the universe. Now, the previous quantum fluctuations put on top of this background of radiation small fluctuations. So both are visible today. The one is the cosmic microwave background itself. The second are the fluctuations on top of it. In other words, if I look at the sky in this direction, or if I look at the sky in the other direction, I see that the temperature, because there is a temperature associated with the spectrum of the microwave background. Well, the temperature, say, is 2.3 Kelvin in one direction, and is 2.3 Kelvin plus, one on 100,000. And this was the first breakthrough result by Kobe, long ago. And then since then, more and more sophisticated experiments have measured these fluctuations to very high precision. They have a spectrum, and I cannot show the slide, but you can see how an inflationary model, which of course has maybe 5, 6, 3 parameters still, so it's still at the model of fitting, but it fits these fluctuations very well, and it's not a simple curve because of various phenomena which happen after the Big Bang. There are modulations, there are oscillations, so-called acoustic oscillations, and it's amazing how the experimental points and the theory match itself. So maybe it's all wrong and it's all an accident, but okay, if you say that this is good evidence that inflation is correct with its origin of fluctuations, then you have to buy the whole thing, and then you can no longer say that the universe was classical even in the very, very early phase. You cannot say that the Big Bang was an infinity in this and this quantities. You have to accept this new paradigm on the Big Bang. And the mystery is still, about what was there before inflation? Was there a beginning of that? Was there another Big Bang? So that's why in my paper I put also an S under parenthesis, because maybe there was a true singularity before, according, for instance, to Hawking. No, there was, time was Euclidean before, at the very beginning. So there are many scenarios. I had my own, but okay, I'm not saying it's better than any other one, but there are many possibilities. And we hope that, you see, the problem is that to address these other questions, you need a theory of quantum gravity. You need a theory which combines general relativity and quantum theory. And there are not so many of them on the market. Okay. So one is string theory. So what is the answer of the string theory gives? Well, unfortunately, string theory is not very easy to solve precisely in those regimes which correspond to the early universe. It's a tough problem, technically very tough. I mean, in principle, it's a well-posed problem. It's not that you cannot ask the question. You can ask the question, but we don't know the answer. So long ago, in the early 90s, I tried to use some new symmetries that the string cosmology has with respect to standard cosmology to argue that perhaps there was an infinite previous phase, preceding the Big Bang or inflation, anyway. And you use the symmetry to relate the present phase to the one which went before.
Could you give some intuition? So string theory, for most people, it's mathematically not approachable, and so as you say, general relativity and quantum theory, we haven't been able to combine them, but string theory has some potential to put these things together. But what is at the very highest level? What is sort of the concept of string theory?
Okay, well, thank you. I mean, this is a very important question, and I think it's true. What you say is true. That string theory, if you really want to say work on it, really do research, it's rather scary from the point of view of technical needs, that. But I think you can explain the basic concept rather simply. Namely, well, the traditional view on elementary particles, of course, the question is what is elementary, because our idea on what is really elementary has been changing over the years. But say, for instance, an electron. So far, we think that it's an elementary particle. It's not composed of something else. So far, who knows? So, for an elementary particle, the traditional view is that it has the same. I shouldn't say it's like a point, but I should say that its degrees of freedom are just the same as if it was a point. Namely, there is a position, there is a velocity of the particle to specify what it is. Then quantum mechanics tells you that you cannot determine both with arbitrary precision, but nevertheless, okay, these are the things which characterize a point particle, okay? Now, the string revolution, if you want, is to say, well, that's not true. If you look with a very, very big magnifying glass into an elementary particle, you test its structure, you find that it is not a point particle with a finite number of degrees of freedom, but it's a little one-dimensional object, a string, which can have ends, then we call it open string, or it can be like a little loop, then we call it a closed string. And now, of course, if you have an extended object, it's not enough to, you have to specify its shape. And so you can imagine that it has many, many more degrees of freedom than a point. Now, why? I mean, it looks like a complication, right? This, say, well, an element, a point particle is much simpler than an extended object. But then the goal of string theory is to say that the different motions, the different vibrations of the string represent the different particles that we know. And maybe many more that are, for instance, too heavy to produce them in a real experiment, because you need a lot of energy to produce very massive particles. So, that's the basic idea, to reduce, it's a little bit like when you say I have the system of atoms, the elementary, the table of all atoms, 92 plus the, and then you reduce this to a system of electrons and nuclei. Okay, so it's this kind of conceptual framework in which it's a bit you economize on this. So, but now here comes the most important point. If your strings are considered as classical objects, namely deterministic, no quantum mechanics, nothing, then they are not that exciting from the point of view of describing what we want, the elementary particles and their interaction. And here the miracle comes. If you add quantum mechanics to the theory of these extended objects, then you discover that necessarily is not something you impose on the theory. Necessarily, there are some vibration modes of the strings which give precisely the elementary particles you need to describe some of the fundamental interactions. For instance, a particle a string which simulates a photon, from a point of view of the theorist, the photon is the carrier of electromagnetic interactions. It's also the carrier of light, but it's also what is exchanged between charged particles and produces their repulsion or attraction. And similarly, a closed string, this is open string, quantized open string, which is a photon. There is another particular quantized closed string, which is a graviton, which is the particle associated with gravity in the same way as a photon is associated with electromagnetism. In other words, this was the important discovery that was made already in the early 70s, that strings force upon you this kind of particles. The existence of these particles is due to the quantization of a string. When we talk about classical things, this doesn't happen. Actually, you find that this violates some bounds, and you cannot have these particles classically. But quantum mechanically, not only you can, but you must have them. And the fact that you must have them, unfortunately, killed this first incarnation of string theory in which I was working, because at that time we wanted to use strings to describe the strong force, the nuclear forces, and the nuclear forces don't like photons or gravitons, with strong interaction. So that was the killer.
So if I understand, ask a question. So if I understand this correctly, Gabriele, so if you go one level down from fundamental particles and go to strings, call them more fundamental, let's call them, and they can now produce any sort of fundamental particle by vibrational modes, by shape, whatever. And there we get a connection to gravity because we could now define graviton that way. Do I understand that correctly?
Exactly. Because one of the lightest strings, actually massless strings, technically speaking, has spin 2. Okay, because this is what characterizes a graviton, the fact that it has a certain angular momentum or spin, and that's, once you have that, you can show by very general arguments that it must produce gravity. The existence of such particles means that any two objects are attracted by the gravitational force, by the Newton law, and so on and so forth.
So it goes away from our classical notions completely, right? So,
yeah,
general relativity is sort of a theory of geometry.
Yeah.
And if we leave that and we go into completely quantum mechanical particles formed by strings, then in some sense our brains are not really wired to think that way, right? We lose all classical intuition to think about that.
You are absolutely right. This is exactly what I keep saying in my talks. It's not, you see, the approach of string theory, again, is upside down. What you learn usually, traditionally, is that there is classical electromagnetism, Maxwell equations, then you quantize it, and then you discover that there is a photon. There are no photons in Maxwell's theory, but if you quantize, light is made of photons. Then you have Einstein general relativity. You quantize, well, you cannot, or at least it's very difficult to get a consistent theory of quantum gravity. But in some rough approximation, you discover that there is a graviton. Now, string theory does the opposite. It does not start with Maxwell or Einstein. It starts with strings. That's it. Then you quantize the string. But it's a rather straightforward thing. It's a little bit tricky, because you have to be sure you get everything right. But it was done already in 1972, and this brings you necessarily to the existence of a photon and to the existence of a gravity. Let's put it that way, simply, and many more things, but in particular. And then you see that classical GR or classical Maxwell theory, general relativity or electromagnetism, come out in the end as a limit of already a quantum theory. So you don't have a classical theory and then you try to quantize. You have a quantum theory to start with, which, by the way, is consistent, doesn't have this infinity, all the problem when you try to quantize general relativity. And then in some limits, you say, but I find something which I can ascribe to a geometry. But the geometrical picture comes after. If you, maybe aesthetically you don't like it, you prefer this beautiful geometrical idea. It has its beauty. I mean, absolutely, I'm fascinated by the beauty of Einstein's general relativity, the curved space-time, and so on. But by the way, in this work we did with thought experiments colliding particles, we never put in general relativity. But by looking at the collision of strings, we find concepts of general relativity like the deflection of light, like the time delay, that there is in general relativity. Also, tidal deformations of objects and so on. All these things which you usually study in the classical theory come out of a quantum theory as a special limits or special cases.
So the classical theories,
you are already at the quantum level.
So it's a way to think about it, Gabriele. The classical theories are approximations. Yeah. So 100,000 years ago, when we were walking around, evading predators and looking for food, quantum mechanics would not have helped us. we had to figure out basic stuff, and so we had to approximate. So most of the classical knowledge or classical theories that we hold today are good approximations to the underlying phenomena, right?
Absolutely. I mean, if you want to study the motion of planets in the solar system, quantum effects are really, really small. So, no, so if your quantum mechanics intervenes at some levels in some places, for instance, in the universe, as I said, it intervenes in the very, very early universe. But then, after has done its job, for instance, after this fluctuation has been produced in the early universe, they become just like classical perturbation. But for instance, okay, one point I often emphasize, going back to the quantum universe before the Big Bang, is that if you had started with initial, like classical initial fluctuations, they would have disappeared after inflation. Because inflation wipes out fluctuation. The reason why with quantum mechanics that doesn't happen is that the fluctuations are continuously produced. Okay, maybe they are also erased a little bit, but they keep being produced because quantum mechanics is there all the time. If you start with initial classical fluctuation, you don't put any quantum mechanics to get rid of them. So, yeah, quantum mechanics intervenes in some places. Of course, it intervenes at the macroscopic level. If not, we will not have atoms and things like this. Huh? So, an atom is not like a small solar system. It's dominated by quantum mechanics. So, so there is this. I think that's also an interesting point, that you don't have to put in the geometry of general relativity from the start, but it comes out as a certain approximation. This is why, for instance, I think that probably the explanation, the resolution of the information paradox, black holes that Hawking has, may be neatly avoided if you start from the start with the quantum theory.
So without knowing a lot about this, Gabriele, are we coming to a point that to make advancements in cosmology, we have to let our classical brains go? It becomes totally a mathematical problem, and we cannot really bring intuition, in anymore. We can't really explain these things on practical terms. Are we getting there? I mean, to go further, it has to be pure mathematics.
Well, hopefully not. I mean, I agree that quantum mechanics has some properties which are far from intuitive, and so I think you have to adjust your your picture of physical reality a little bit differently. Where you can superimpose different states and so on and so forth. It's true. It's not the most intuitive theory, and who knows? Maybe also quantum mechanics will one day be explained in more natural ways. Einstein himself was not too hot about it, and but it seems that it works to an amazing degree, and there have been now good tests of these Bell inequalities, which typically
Our brains might become quantum mechanical, Gabriele.
yeah.
Maybe 100 years, 200 years from now, we may have a different brain arrangement potentially.
You see, fortunately for, as you said, for everyday's life, for the reality that surrounds us, classical physics is enough. Is enough, provided that this I don't know, this piece of material has this weight, has this mass, has this volume. You don't have to know why, but if you ask really why, you find out that you need quantum mechanics. But if you take it for granted, and you say that's a phenomenological parameter. I know that the density of water is this. You can carry on. But okay, in principle, quantum mechanics will tell you why the density of water is such and such, and why the density of lead is so much bigger, and so on and so
Yeah.
forth.
So we have to go further and further, deeper in that direction to get to more fundamental questions answered. I just want to touch on another. I think you're turning this into a book. So high energy collisions of particles, strings, and branes. So it's a series of lectures here. You say in these lectures we will use very high energy to expose in clear ways some of the deep conceptual problems that seem to emerge when one tries to combine the basic principles of general relativity and quantum mechanics. And that's what we've been talking about. So we talked a bit about particles and strings. What do you mean by branes?
Okay, branes are something introduced a little bit later, mainly by Joe Polchinski, unfortunately, the late Joe, which, okay, technically speaking, they correspond to the following idea. I mentioned the concept of an open string, a string with ends, okay, with two ends. Now, Joe Polchinski realized that you can do two things about the ends of an open string. One thing is to let them free, move free. Then you find that they have to move with the speed of light, the ends, and so on and so forth. And this was the classic, the typical thing that everybody was doing until then. But then he realized that you can do something else. You can pin down the end of a string, fix it. At least fix it in some directions. Okay, for instance, it has to be, I don't know, on this horizontal plane. It can move in the plane, but it cannot go up and down, for instance. Okay? Then, and this is also a perfectly consistent theory of open strings. Now, at this point, the ends of this open string stay on some surface. For instance, the horizontal surface of this table. They don't go up and down. Well, okay, this surface of my table is a brane or is a membrane. It's a higher dimensional order. It's no longer a string because, for instance, my table is two-dimensional already. Okay, and then it itself can have its own motion, its own dynamics, and so on. So so now this object have played a very important role in developing string theory. Now I will not go into any details, but what we looked into in that paper was how an open string interacts. Sorry, a closed string. A closed string will not be attached to a brane. Only open strings are. So I take a closed string, like a graviton, as I said, and I make it collide with this object, with this brane. And what can happen, for instance, is that this closed string touches the, the, the brane and opens up. Well, this is well known that a closed string can open up, can break and form it. And if it touches the brane, it will convert itself into an open string of that type, okay, with its ends attached to the. Now, you ask me why are we interested in this? Well, this is very much related to beautiful work which was done by Juan Maldacena many years ago. I think it was in 94, something like this, in which he realized a very interesting connection between a theory of gravity and a theory without gravity. And the interesting thing is that the theory of gravity, which is related to closed string, lives in all the space. And the theory without gravity has only these open strings, if you want. And that theory is defined on this brane system. Now, this seems to be a curiosity, but has been proven extremely successful and productive as an idea, because it can relate a theory with gravity to a theory without gravity, a theory a little bit more like electromagnetism. And there is a dictionary for a given problem in gravity, you find a related problem in what we call a gauge theory, but that's a technical one, in this theory without gravity. And sometimes a difficult problem in one case can be mapped into an easy problem in the other. And so, and this construction of Maldacena uses, in fact, a stack of these D branes. You don't have just one, but you put many, many of them, and then you define this system that lives on these branes, and which is an ordinary theory without gravity. And for instance, it's also on this basis that people have made a lot of progress, for instance, understanding the entropy of black holes. It turns out that one of these brane systems can be shown to be black in the sense of a black hole, and you can compute exactly its entropy. I don't know if you are familiar with this. I mean, there's a famous Bekenstein-Hawking entropy for black holes, and this model has given a statistical mechanics interpretation of entropy, because entropy is a thermodynamic concept, but when you do statistical mechanics, you have a microscopic understanding in terms of degrees of freedom of the system and or number of states. And two guys from Harvard, Strominger and Waffa, have shown in one particular case that they could reproduce this way exactly the entropy, the Bekenstein-Hawking entropy of black holes. So that gave a big push to the idea that the original claim of Hawking, which I think he himself retracted later, that information is lost in a process in which you form a black hole and then the black hole Hawking radiates, disintegrates by the Hawking process, information is still preserved, unlike what he was saying in 1974. Now, in fact, one aim of our Gedanken or thought experiments was precisely to see whether we could understand this conservation of information in a process which is quantum from the beginning to end. So this goes back to the idea of not putting in too much classical stuff from the start. We want to do the calculation fully at the quantum level, then maybe in some approximation it will be like, close to a classical.
So on the branes,
somehow preserving information.
Yeah, so on the branes, Gabriele, so do I understand that there are no closed strings? They're all open strings on the brane object?
Yeah, in other words, the closed strings can leave the brane. In fact, even an open string, if its two ends are on the same brane and the two ends meet, they free themselves from the brane and fly off. So you have to, this is precisely what we have studied in those papers. There are processes in which either a closed string hits the branes and becomes an open string. But then the reverse process is also possible. An open string with two ends on the brane can fly out of the. So, in other words, there is even a brane world scenario where our universe is a brane. Namely, I didn't say this, but another very strange peculiarity of string theory, of quantum string theory, is that it requires extra dimensions of space. Namely, for some reasons, which we don't quite understand physically, but mathematically quite sure, is that you cannot have a consistent string theory in a 3+1 dimensional space-time. In our usual space, three-dimensional space+time. The most interesting string theories want 9+1 dimension. So, now of course you can say, okay, so then we can throw the theory to the wastebasket because, okay, we don't live in 10 dimensions. But of course, theorists are more smart than that. So they invented ways out. You have to assume that the extra six dimensions of space are very small and so not really directly visible. They are really like little circles which have the same size as a string itself. And that gives some very interesting physics. However, there is an alternative, and the alternative is that all these dimensions are big, including the 6 extra ones, but our universe is, we live in a sub-manifold, what is called a sub-manifold, a 3+1 dimensional sub-manifold, which is a brane, in which there are electromagnetic weak and strong interactions, and gravity is weak because gravity lives in the whole space, also in the extra dimension, because it's carried by these closed strings. So this is what is called the brane world scenario, and there have been many. There have been even ideas of how to test this with experiments, because when you have a collision of particles, maybe some energy escapes with this extra dimension, so you should see it. For the moment, there has been no clear evidence for this scenario. So I think most people bet rather on the fact that the extra dimensions are very small, and so you see only indirectly their effect. This idea, by the way, goes back to old work by Kaluza and Klein, who even convinced Einstein that there was a possibility to explain at the same time gravity and electromagnetism if you introduce one extra space dimension. Then gravity in this 4+1 dimensional universe will look like usual gravity plus electromagnetism. But the extra dimension had to be a little circle, cannot be infinite. So, and string theory can use the same idea, adding to it beautiful things like the fact that these extra dimensions cannot shrink to zero, has a minimal size, like a string cannot shrink to zero, must have a minimal size. So all these things, they add more structure to this old idea of Kaluza and Klein.
So Gabriele, in conclusion, you have been with string theory right from its beginnings. It has gone through a lot of revolutions, a lot of new ideas, and very complex mathematics. We haven't been able to really I don't know if this is true. We don't really have any testable hypotheses or testable predictions from it yet, right?
Yeah, you can say that there is certainly no smoking gun in favor of string theory. That, in my opinion, is mostly due to our difficulty in really extracting reliable predictions. I mean, besides, say, the existence of a graviton, the existence of a photon, and so on and so forth, to really, compute things to the level at which you can compare them with present experiments is still hard. For instance, there is a whole, sector of string theory which is called string phenomenology, which aims at finding solutions of string theory which look like the so-called standard model of elementary particles, which works very well. So the hope there is to not only reproduce the standard model, but also to predict some of the 20-some parameters that are still, put in by hand in the standard. It works very well, but it still has some 20-some parameters, and we don't understand the hierarchy of masses and so on and so forth. So the truth is that string theory is pretty unique, but its solutions so far are very, very many. Namely, it's like you have an equation which has zillions of solutions. For instance, many of these different solutions come precisely from what you do with these extra dimensions. If you do something, then you get some prediction. If you do something else, you get other predictions. And maybe not all this, what we call compactifications of the extra dimensions, are really consistent at some high level of precision. And we don't have yet that level of precision. But even then, it would be beautiful if we could construct at least one solution which looks like our real world. It's consistent with experiments, and maybe it goes a little bit beyond because, for instance, it incorporates also gravity at the quantum level. So this I keep telling my my friends at string conferences, please work on that. I mean, I was at the string conference this year, of course, on Zoom, not in person. And I think now the string community is saying, yeah, maybe we should, there is lots of beautiful mathematics, but we should remember that we are physicists and we have to deal with the real world and try to make predictions. Now, you see, for instance, look at the old string theory. The old string theory that I was talking about, that was, dismissed, okay? Falsified, okay, that's a word. Was falsified very quickly. In 5 years, because, okay, I wrote my model in 68, by 74, 73, it was clear that this was not a good theory because it predicted these massless particles and nobody had seen them in the world of strong interaction. Now, the new string theory, for instance, predicts not only a graviton and a photon, which are beautiful, but it has also a scalar massless particle, which is called the dilaton. And if that particle remains massless after the theory is solved completely, because for the moment it's massless, but the theory is not solved completely, then you can prove that it leads to violations of the equivalence principle, namely to the universality of free fall, by a large amount. So there are already bounds on how heavy that dilaton has to be in order not to exclude that string theory. So this is to give an example of possibilities to falsify string theory. There are many possibilities, right? The old one was falsified within a few years. This one is harder, but it's not true that string theory cannot be falsified.
It's
But of course, you need to do calculations to the predictions to the right level of.
yeah, it's exciting. As you say, there is nothing else. There is nothing competing in the marketplace.
That is true. That is true. Well, there are some alternatives like loop quantum gravity, but I don't think they have the same level of ambition also. And they
in
look
some
to
sense,
me.
Gabriel, it seems to me that you should pick one and start calling it the standard theory, the standard model of string theory, and let the classical folks try to falsify it. The problem with string theory, in some sense, as you say, is the multifactorial possibilities,
Exactly.
which is
The number of possibilities is huge. However, okay, most of the solutions that you can find do not resemble the real world. Now, there could be, solutions which are realized in another part of the universe. Who knows? But okay, we would like to find one which fits our experiments here and now. Okay. By the way, there is another thing, for instance, that could have been a smoking gun for string theory, is that the so-called fundamental constants that string theory has, like you may have heard about the fine structure constant, which is numerically 1/137, more or less. Okay, those constants, which in usual theories are really constants to be measured, in string theory they appear to be dynamical, namely they are related to some values of some fields. So they could vary a priori in space and in time. So people have looked for variations of alpha, of this fine structure constant, in time, by looking at old data, cosmological data, and found no evidence. But if there had been some evidence for variations of fundamental constants, that would fit perfectly well in string theory and not in any conventional field theory, but standard quantum field theory. So, but to be honest, there has not been. Now, there is one doubt I have, to the risk of not being very popular in the string community. I will make the statement. The doubt can come that what we now apply string theory to, which are the particles we know today and we think today to be elementary, are not really elementary. Namely, we made that mistake, if you want, in the early days because we thought, I don't know, that the pion was a string. In a sense it is, but actually it is a bound state of a quark and an anti-quark. So now the new string theory says, okay, fine. So I say that the quark is a string. But who says that the quark itself is not a composite object of other things? You see, one of the axioms of string theory is that there is nothing more elementary than a string. A string is it. I mean, it's not that you say, well, a piece of string is something. The whole string is the most elementary thing. So, maybe in other words, we have to assume that no other structures, substructures of elementary particles are there between the length scale that we can measure today, we can see today up to a certain size, for many, many, many orders of magnitude, you have to assume that there are no further structures in your elementary particle world. And now, this historically seems to be hard to believe, because if you think of the layers there are in nature between macromolecules, ordinary molecules, atoms, and then the nuclei, and then the nucleons inside the nuclei, and then the quarks inside. The history of physics has told us that the closer we look, the more structure we see. And now everything should stop at the level we know today. So there is a little doubt.
Yeah, I mean, what we call reality might be just a classical confusion. Yeah. There may not be anything there that is other than strings, as you say. But the field, it is attracting more people to come into the field, it looks to me, and perhaps we get better tools. If there are some plausible predictions, it can really take off, I think. But it just the sheer complexity or the possibilities around it makes it very hard, right?
Well, I mean, young people are still very attracted. I mean, when you go to a string conference, you see that the average age of the participants is below what you see in other conferences. I'm talking only about theoretical physics. Now, it's because there are lots of things you can do in string theory. It opens up enormous possibilities of looking at different things and so on. To do, say, formal mathematical work, it's relatively easy. You can also make up your name if you find something. So it is an attractive, and I must say that the new generation of theories that do string theory is impressive from the technical point of view. They really master mathematics and so on. I mean, you see, at some early stage of your career, I mean, you can learn things fast and become. However, I think probably to make real progress in the field, you need maybe some new physical insight, some new physical idea, and particularly, to concentrate on making predictions which are reliable and then can be indeed verified or falsified. We can never really fully prove that the theory is correct, but you can falsify a theory. And if you cannot, then it becomes really not so interesting. Yeah. But in principle, for instance, also this early universe is another place where you can try to make predictions. So if we could study the dynamics of the early universe in string theory, and then this dynamics is brought to the present in the form of structures at large scale and so on, or tensor perturbations, gravitational waves be measured and so on, that would be also a very interesting
excellent
where to test theory. Okay, the theory, if you want, is still a little bit in its infancy, although it's more than 50 years. Okay, the new one not as much, but still a few decades. But it's not an easy enterprise.
Excellent. This has been great, Gabriele. Thanks so much for spending time with me on a weekend.
Thank you for having me. Okay, I wish you everything.
Thank you.
Bye. Okay, bye then.
Bye.